All right, in this video, we're going to talk about Section 7C, which is the law of large numbers. Okay? So here we're going to talk about what the law of large numbers are, and we'll look at some examples related to that. Okay, the law of large numbers applies to a process for which the probability of an event A is, of course, P with the A in the parentheses, and the results of repeated trials are independent. Now, if the process is repeated through many trials, the proportion of the trials in which event A occurs will be close to the probability of event A. The larger the number of trials, the closer the proportion should be to the probability of event A. So here we're going to illustrate the law of large numbers with a die rolling experiment. The following figure shows the results of a computer simulation of rolling a die. And this is what it looks like. Here are the proportion of ones here, and then the number of rolls here. Okay. Now, here, of course, the proportion of getting a 1, or the probability of getting a 1, will be 1 out of 6, or 0.167. Here, that's why you see that vertical line going straight across. And based on this, the more that we roll a fair die a certain number of times, then we're going to get closer and closer and closer to the actual probability of event A. And in this case, the probability of rolling a 1. Okay. Now, in example 1, it says, suppose you toss a fair coin 10,000 times. Should you expect to get exactly 5,000 heads? Why and why not? And what does the law of large numbers tell you about the results you are likely to get? Okay, so should we expect to get exactly 5,000 heads? Well, the answer to that would be obviously not, because in this case here, we can't count precisely the number of heads. Well, actually, we can't predict precisely how many heads will occur. Okay, we can't come up with a precise prediction of how many heads will occur, so it will be this answer choice here. And on the next page, what does the law of large numbers tell you about the results you're likely to get? Okay. Now, based on that particular situation, based on the law of large numbers, if you increase the number of tosses, then the proportion of heads should be getting closer and closer to 0.5. Okay, because the probability of getting a head will be one half, or 0.5. So if you do it multiple times, if you increase the number of tosses of a single coin or of a fair coin, then the proportion of heads should be getting closer and closer to 0.5. Okay. All right, next we'll look at expected value. Okay. This is also used in probability. Let's say we want to consider two events, each with its own value and probability. The expected value will be the value of event 1 multiplied by the probability of event 1 plus the value of event 2 times the probability of event 2. And this can be extended to any number of events by including more terms in the sum. That means you could have like 3 events, 4 events, 5 events, as long as each event has its own probability and its value. Okay? So in example 2, we'll start with this. You are given 2-to-1 odds against tossing 3 heads with 3 coins, meaning if you win $2 if you succeed, and $1, and you lose $1 if you fail. Find the expected value to you of the game. Would you expect to win or lose money in one game? And what about in 100 games? And explain. Okay, let's start off with the expected value for this game. Okay, now there are a couple of events here that we have. Okay, now I'm going to have to do the work at the bottom here. Your first event, event number 1, will be to toss 3 heads. Okay. And then the second event, let's say you fail to toss 3 heads. Let's say you toss at least 1 tail. In fact, if you don't know this, those two are the complements of each other. That means we're tossing 3 heads mean that you're tossing no tails. This one is tossing at least 1 tail. Okay, let's find the probability of each one of those. So here, the probability of getting 3 heads and you're doing this with 3 coins, by the way. So on the first coin, that's going to be 1/2, that probability. On the second coin, 1/2. And on the third coin, 1/2. Okay, now these are independent of each other, so we're multiplying 1/2 times 1/2 times 1/2, which will give us 1/8. And then find the probability of tossing 3 coins and getting at least 1 tail. Well, if the probability of 3 heads is 1/8, then the probability of at least 1 tail will have to be the complement of that. So here we can do 1 minus 1/8. If you recall in the last video, we use the at least once rule. So it'll be 1 minus that probability. So 1 minus 1/8 will give us 7/8. Now, again, if we want to do this on the calculator, we can clear this out, 1 minus, and then in parentheses, 7 divided by 8. And that will give you the decimal value of 0.125. 1 minus 1/8. That'd be 0.875. And then change that to a fraction. We press the math key and then select menu item number 1. And that will give you the 7/8. Okay. And now we're going to find the expected value. Okay. So I'm going to have to do this at the bottom of the sheet here. To find the expected value, okay, it does say in the problem, if you succeed, you win $2. So this will be a positive $2 times the probability of getting 3 heads will be 1 out of 8, and then plus you lose $1 if you fail. So if we lose $1, that's going to be a negative $1 times the probability of getting at least 1 tail, 7/8. Okay. So in this case here, on the calculator, we're going to do 2 times, and in parentheses, 1 divided by 8, close parentheses, plus negative 1. Now the negative key is at the very bottom of the calculator here. It's way down here. Don't get that confused with that minus sign up front on the right side. So it's -1 times, and then left parentheses, 7 divided by 8, close parentheses. Now we're going to round this up to 2 decimal places as indicated here in the problem. So this will be -0.63. So in reality, we can expect to lose 63 cents based on that gain. So to fill in this, now they do have the answer choice of a minus sign and a plus sign. Since it's negative, we choose the negative sign, and then 0.63. So we would expect to lose 63 cents if we play this game in one game. So here, based on these choices of answers here, I would expect to win or lose money in one game. In this case, I have to pick this one because I would expect neither, because the outcome of one game cannot be predicted. So he was just dealing with only just one game, and we can't make a prediction on that. Okay, and would you expect to win or lose money in 100 games? Well, if we play that game 100 times and we keep losing 63 cents, okay, I would expect to lose here because that expected value is negative. Okay. Okay, let's look at another example of an expected value here. In this case, suppose someone gives you 13 to 4 odds that you cannot roll 2 even numbers with the roll of 2 fair dice. This means you win $13 if you succeed, and you lose $4 if you fail. What is the expected value of this game to you? Should you expect to win or lose the expected value in the first game? What can you expect if you play 100 times, and explain? Now, there is a table that will help you find the required probabilities. It's down here. Okay, there's an icon in the homework that you can click on, and you'll get this particular table here. All right, so now let's try to answer what will be the expected value of this game to you. And there are 2 events that we're going to be dealing with. The first event is going to be, in this case, rolling 2 even numbers. The second event is not getting 2 even numbers. So we'll just say not roll 2 even numbers. For each of these cases, we're going to find the probability here. So for rolling 2 even numbers, that probability of 2 even numbers. Now, looking at this table right here, we have to find out which one will give us an even number. Okay? When you roll 2 dice, you get a sum of an even. That sum has to be an even number. So we need to pick out which one of those probabilities, which one of those will give us an even number. Well, by looking at this, I see one of them, and I see another. 1 plus 5, that's 6. I'll go back to that 1 plus 1, that gives us 2. And in this case, 2 plus 2, that gives us 4. 2 plus 4 is 6, and 2 plus 6 is 8. Okay. actually two even numbers. They have to both be even. So I need to, unfortunately, eliminate anything that has an odd number in it, and only include the 2 plus 2, 2 plus 4, and 2 plus 6. Well, I know the 3 is odd, that's not going to work. But for 4, I can only include 4 plus 2, 4 plus 4, and 4 plus 6. And then I know I can eliminate the 5. But for the 6, 6 plus 2, 6 plus 4, and 6 plus 6. Because both numbers have to be two even numbers. They have to have the sum of two even numbers, not an odd and an even, or an odd and an odd. So here, the ones that I circle, there are 9 possible outcomes here. So the probability of two even numbers would be, in this case, 9 over 36. Now, if you take 9, divide that by 36 on your calculator, you will get 0.25. So the probability of rolling two even numbers will be 0.25. Now, for not rolling two even numbers, that would be the complement of rolling two even numbers. So that's going to be 1 minus the probability of rolling two even numbers. That's going to be 1 minus 0.25, which will give me 0.75. Okay. All right, now let's find the expected value here. That's going to be this. If we win, let's go back up here. If we win, we get $13. And if we fail, we lose $4. So here, that's going to be the $13 times the probability of getting two even numbers. That would be 0.25 added to. Now, if we lose $4 if we fail, that 4 has to be a negative 4 times the probability of not getting two even numbers. That's 0.75. Okay, so now, in this case, we're going to do, let's say 13 times 0.25 plus, and then negative 4 times 0.75. Here we're going to get a positive 0.25. So that expected value here will be 25 cents. So in this case, to answer what is the expected value of this game to you, it would be 25 cents. Okay, and now, should you expect to win or lose an amount equal to the expected value in the first game? Okay, the answer has to be no, because this is only one game and the outcome can't be predicted on just that one game. But the next part is, what can you expect if you play 100 times? Well, if our expected value is 25 cents, and if we play it 100 times, so 0.25 times 100 would give us $25. So if we play this game 100 times, we can expect to get $25. Not saying that you will, but we can expect that much. And then we can explain that particular result. Average over 100 games, you should expect to either, and this is going to be one of the answer choices here that you have to choose from the drop-down menu, win or lose. We can expect to win that $25. Okay. So that's how we answer that particular problem. Okay. All right, let's look at the next example of expected value. An insurance policy sells for $800. Based on past data, an average of 1 in 100 policyholders will file a $15,000 claim, and an average of 1 in 250 policyholders will file a $30,000 claim, and an average of 1 in 400 policyholders will file a $60,000 claim. Find the expected value to the company per policy sold. If the company sells 10,000 policies, what is the expected profit or loss? Okay, so now let's look at these events that we have here. Okay, the first event is where the insurance policy is sold by the company for $800 here. That would be event 1. I'm going to say here insurance sold at $800 with a, not profit, a probability, and I'm going to abbreviate the word probability of 1. The probability of them selling an insurance policy at $800 will be 1. Now event 2. The company is going to pay $15,000 with a probability of 1. Not 1. Because it says here, an average of 1 in 100 policyholders will file a $15,000 claim. So that's going to be 1 in 100. And that's going to be a negative value because the company is going to pay out that particular amount. And then event 3, let's say the company pays, in this next case, a $30,000 claim. But this time, the probability for that was, let's say 1 in 250, so it'll be 1 out of 250. And again, it's going to be a loss to the company because they have to pay out that money. And then finally, event 4. The same company pays, and this time $60,000. And the probability of that happening would be, in this case, 1 in 400. So it'd be 1 out of 400. And again, that's going to be a loss to the company as well because they have to pay that $60,000 claim. Okay, now let's find out what the expected value is going to be. Okay, that's going to be this, $800. The insurance is sold. The insurance company sells that to the individual. That probability is going to be 1. So that's going to be $800 times 1. And then plus, now the company is going to pay $15,000. So that's going to be a negative $15,000 times its probability of 1 over 100 plus. And then the third event is where the company pays $30,000. That's going to be negative as well. So we got negative 30,000 times 1 over 250. And then plus event 4, $60,000. Oh, that's going to be negative because the company is going to pay out that $60,000. So it'll be negative 60,000 times 1 over 400. So now we're going to find out what that expected value is going to be. Clear this out. Okay, y'all going to excuse me for putting this calculator over the paper. So here I'm going to do left parentheses 800 times 1, and then plus left parentheses negative 15,000 times 1 over 100, 1 divided by 100, close parentheses, and then plus left parentheses negative 30,000 times 1 divided by 250, close parentheses, plus, and then left parentheses negative 60,000 times 1 divided by 400. And we're going to end up with 380. So our expected value would be $380, okay, for that insurance company. And it is a positive number. So here, the expected loss or profit, they're going to give you that choice. In this case, it's a positive number, so it is going to be a profit. And then we want to find out if the company sells 10,000 policies, what is the expected profit or loss? It is going to be a profit. So if we sell 10,000 policies, your expected profit is going to be this. We take 10,000 policies, multiply that by the $380, you'll end up with $3,800,000. Okay? So here, by selling 10,000 policies, the company will have a profit of $3,800,000. Okay? So that's how we calculate an expected value here. Okay, let's talk about house edge. Okay, this is something that's found in gambling houses and casinos. Okay, here gambling houses and casinos generally have games set up so that the house always has a higher probability of winning than patrons. For any particular game, the house edge is the expected value to the house of each individual bet. So like in example 5, average over all games and all bets placed, the house edge of a particular casino is 0.018 per dollar gamble. If a total of $114 million is wagered in the casino over the course of a year, what is the casino's expected total gain? And explain. Okay. Now here they got this all kind of laid out for you in a sentence when you give your answer. Okay. Now here they tell us that the casino can gain. Okay. If you look at it, that's going to be 0.018. They give us that. Okay. Now here they're going to give you the choices of answers here. And obviously you'll pick the one that says 0.018 or whatever they have and not the percent. Okay. So the total gain is either the product, the sum, or the average. And in this case here, we're looking at the product. Okay. The product of course, the house edge, which is that amount, and the amount wagered in a year. That's pretty much what you'll select. And now we're going to find out what the casino's expected gain is for the year is going to be. Well, if we look at the expected gain, then we're going to take this amount of 0.018 in dollars. Multiply that by, they say $114 million. That's actually going to be 114. And I know 1 million has 6 zeros behind it. So it's going to be 114 with 6 zeros behind it. Okay. And now we're going to find 0.01a. Multiply that by 114 with 6 zeros. It will give you this amount. $2,052,000. So for this casino's expected gain for the year, it would be $2,052,000. Okay. Okay. Here's the last example of expected value dealing with the lottery. A lottery posted the probabilities of winning each prize and the prize amounts as shown in the chart to the right. Suppose that one lottery ticket costs $1. Find the expected value of the winnings for a single ticket. Then state how much you can expect to win or lose each year if you buy 10 lottery tickets per week. And should you actually expect to win or lose this amount? Okay, so now let's look at what we have here. Now we're going to find the expected value for the first prize, second prize, and third prize. Okay, let's start up with the expected value for the first prize. And first prize is the amount of $1 million. And then we're going to multiply that by its probability, 1 in 60 million, 1. So it'll be 1 over 60 million, 1. To calculate, what I'm going to do here is do 1 million and divide that by 60 million and 1. And I'm going to round this up to, let's say, 6 decimal places. This will be 0.016667. I'm going to try to use as many decimal places as I can to come up with the expected value here. And then for the second prize, the second prize is $100,000. To find that expected value, I'll take that and multiply that by the probability here, which is 1 in 30 million, 1. So I'll do 100,000, 1 with 5 zeros, divide that by 30 million, 1, and then hit enter. To 6 decimal places as well, that would be 0.003333. And then for the expected value for the third prize, which is $1,000, that'd be 1,000 times its probability. 1 in 15 million, 1. So it'll be 1 over 15 million, 1. And I'm going to do the 1,000, and I'm going to divide that by 15 million, 1. Okay. I did this before, but that's actually going to be 0.000067. And the reason for that is that decimal point and that e to the negative 5 means 10 to the negative 5. So I need to move the decimal point 1 and then 4 more places in front to get that amount. So I'm going to use that right here. Now, let's think about this for a moment here. The cost of a ticket was, one lottery ticket costs $1, as indicated in that example. So here the cost of the ticket is $1. And if you're paying for it, then that means you're losing $1. So the expected value of the ticket is a negative $1. Okay. So now let's look at the total expected value of all of this. The total expected value here is this. We're going to add each of those individual expected values here. The 0.016667 plus 0.003333 plus 0.000067 plus negative 1. Okay. So if I add 0.016667 to 0.003333 plus 0.000067 plus negative 1, I'm going to end up with, and I'm going to round this up to 2 decimal places, which is to the nearest cent. That's going to be negative 0.98. So that expected value will be a negative 98 cents. Okay. So that would be, and they already have the dollar sign, he just put in negative 0.98. Okay. Now, the other part of the question is this. If you buy 10 tickets per week, you can expect to either win or lose how many dollars each year. Okay? Now let's think about this for a moment. You're buying 10 tickets per week. Now in a year, since we're trying to find out what this is for the year, how much we lose win or lose for the year, there are 52 weeks in a year. So it's got to be 52 weeks divided by 1 year, and I know the weeks are gone. And guess what? The expected value is at negative 0.98, so I'm going to go ahead and multiply that by negative 0.98. And this is going to be per 1 ticket. So we can expect to lose 98 cents for every 1 ticket that we buy. And the tickets divide out. I can multiply 10. I'll tell you what, I'll take that number right here since I want an accurate number. That number times 10 times 52. And in this case, we're going to round to the nearest cent. Or better yet, let's do this. Better yet, 10 times 52 times negative 0.98. That would be negative 509.60, or negative $509.60. Okay, so if we buy 10 tickets in a single year, 10 tickets per week, we can expect to lose this amount, $509.60 without the negative sign each year. Now, you would or would not expect to win or lose this amount Here we would not. And that's because there's no combination of prizes that equal that amount. Okay? So that's very important there. Okay? So we would not expect to win or lose because of that. No combination of prizes equal that amount. Okay. So here, this will complete that video on the law of large numbers.